All right, sound check, sound check. Audio is working fine. Let's check for video now. And I see the video footage playing back. Okay, I think we are good to go. Let me mute that. Let me unplug this headset and put it away, and let's get started. All right, so yesterday was quite something for those who actually got to see glimpses of it. But yeah, I underestimated how much a runny nose could interfere with my lessons, and I also underestimated how quickly it could get worse. So I attempted to do this yesterday, and about an hour into it, I just couldn't anymore, and I decided to just scrap it, and we're just going to redo everything today, and hopefully this will be our only instance of having to postpone a lecture, although, you know, you can't really guarantee that sort of stuff in life. But I will try to keep things consistently on Sundays. So the plan for today is to just do mixed kinematics problems from both the purely horizontal problems and the purely vertical problems, and we will end off with a problem that mixes both. And that will kind of be our segue into our next unit, which will be the topic of projectile motion. And I don't plan on starting projectile motion today because I kind of just squeezed this into my schedule. And yeah, I'm going to be busy and I have to keep this under a certain amount of time. I've got other stuff to do this evening. So I guess we should not dilly-dally, and yeah, let's just get started. So last time I left you guys off with a problem about a rocket. It was initially launched at 50 meters per second straight upward. I drew a path that doesn't go straight up and straight down because, you know, making it wider while it's not really moving horizontally over here, widening this diagram helps with just giving you more space to write things in. So that's why I draw things that way. If we wanted to draw the path more realistically, we would just draw a straight line up and a straight line down, and you know, it's not very helpful when you draw it that way because it doesn't give you a way of visually separating the upward part from the downward part of the motion. So for those who were questioning that from last week, there's your answer. Yes, I know that this isn't the correct shape of the trajectory over here. It's not supposed to be an upside down parabola, but we draw it that way for the sake of easy visualization. And going back to the problem, so rocket launched straight up at 50 meters per second. It's rocket propelled in such a way that it overcomes gravity and has a little bit of acceleration left over, such that it accelerates at 2 meters per second squared upward for some amount of time. Let me find the problem. It says a model rocket is launched straight upward with initial speed 50 meters per second. It accelerates with a constant upward acceleration of 2 meters per second squared until its engines stop at an altitude of 150 meters. until its engines stop at an altitude of 150 meters. So launched at 50 meters per second with an acceleration. I guess I will do that in red. Wow, where did that come from? With an acceleration, I will call this A1 of 2 meters per second squared. Let's call this V0. I want to split this into 3 different segments of motion. And the rocket goes up for 150 meters before its engines are cut off, runs out of rocket fuel or whatever. So that's the first 150 meters. And from that point on, no rocket propulsion, it's all gravity. So it's already heading straight up at this point. So gravity is gonna slow it down as it continues to rise. It's gonna reach some sort of maximum height. And then it's going to come back down to ground level. And we are tasked with finding what is the maximum height? What is the maximum height that it reaches? B, how long after liftoff does the rocket reach its maximum height? So the total time to rise, as I like to call it. And part C, how long is the rocket in the air? So that's what we called the hang time from last week. Hang time, total time that an object is in the air. Those are the 3 things we are tasked with finding. So I do not know in advance what the maximum height is going to be, which is why we should not assume that this drawing is to scale. The way I've drawn it, it looks like this, the change in height from here to here, it looks like it's a little bit less than 150. That may turn out to be the case, or it might not. We can't be faulted for getting our proportions wrong in our diagram if we don't have that information ahead of time. You will never lose points for not drawing things to scale if you're not given enough information up front to be able to draw things to scale. You don't get penalized for that. So let's go ahead and figure out how I want to piece this together. First of all, I want to call this 150 meters. It's an increase from a height of, we'll call it 0 to a height of 150. So that's a positive delta y. I'm going to call it delta y1. And I want to split this into 3 phases. I want to do phase 1 is from launch to here. So whatever velocity we have at this point, that's going to be v1. Then the next segment is going to be from here to the top. The reason you want to choose the top, the reason you want to choose the peak of an object's trajectory is because it gives you a free piece of known information, which is the fact that the vertical velocity at the top is going to be 0. It's changing from an upward velocity to a downward velocity. It's changing from positive to negative. If you want to do that on a continuous basis, you can't skip numbers. You have to go through 0. So that is going to be my V2. I guess I will arrow to it right there. So that's going to be my V2, which is equal to 0. And some people might be tempted to pick this point next, but you don't actually need this. if you wanted to take advantage of symmetry, I suppose some people will skip going to the top and will just go directly from this point where V1 is marked to this point. But you don't actually need that, and it's going to end up wasting more time than it saves. So my third point, my third segment of this object's movement is just going to be the rest from the top all the way to the bottom. Great, my nose is already acting up. I've been fine all day. And now my nose is angry at me. Here's hoping it doesn't escalate to the point that it reached yesterday. Anyway, over here, I would call this V3. And let's go ahead and organize our information. So, first segment, first phase of the motion, first leg of the rocket's trip, whatever you want to call it. We've got V0, which is 50 meters per second, V1, which we don't know yet. Acceleration for phase 1 is positive 2 meters per second squared, since we are considering up to be our positive direction. Delta Y1 is given as 150 meters, and T1 is currently unknown. That's 3 pieces of information. We have enough to calculate the other 2. As long as you have 3 of these 5, you can always calculate the other 2. Next phase, we'll start with V1, end with velocity V2. The acceleration for phase 2, this is the point after the rocket engine is cut off, so the only thing accelerating this rocket would be gravity. And we're neglecting air resistance. If we weren't, then that would be something to concern ourselves with. We'll talk about air resistance when we get to... Well, we'll talk about it conceptually when we get to projectile motion. And we'll talk about it a little bit more when we get to the force chapter, or as some students call it nowadays, dynamics, because we have to make it sound all cool. Anyway, negative 9.8, negative g, negative 9.8 meters per second squared for the acceleration. Displacement for phase 2, we currently don't know. And time for phase 2, we don't know. We do know V2 is equal to 0, so let's fill that in. And phase 3, from all the way up here to all the way down here, it'll start with velocity V2, which we know to be 0. It'll end with velocity V3. We don't know what that is yet. The acceleration for this phase is the same as it was for the previous phase. It's negative g, negative 9.8 meters per second squared. And then delta y3 we do not know yet. And t3 we do not know yet. Okay. So, we need to calculate, first off, the maximum height that is reached by this rocket. And to do that, we need to figure out the change in height from this point to this point. That is, we need to find delta y2. We are looking for delta y2. We are looking for delta y2. I guess I'll draw it with an upward arrow, delta y2. Come to think of it, I probably should have drawn delta y1 with an upward arrow as well. Displacements are vectors after all, their direction matters. Okay. So, to get delta y2, well, I need 3 pieces of information for the second phase. And I only have 2 right now, so I need a 3rd piece of information, and I can get it from here because V1 is a variable that phases 1 and 2 have in common. So if I solve phase 1 for v1, I can then plug it in here to get delta y2. So that's going to be my target for now. We need to find v1. And if we know v0 and a1 and delta y1, which equation would be the best one to use here? I believe it would be the third. And the reason is quite simple. The third equation involves all 4 of these variables, and it doesn't involve time, which is great because we don't know the time yet. So the third equation would be our best bet. We know 3 out of the 4 variables that the third equation uses. That just leaves 1 out, which we can solve for. So v1 squared, that would be the next velocity, equals the previous velocity squared, plus 2 times the acceleration for that phase times the displacement for that phase. v1 squared, we do not know what it is yet, equals 50 squared is 2500, plus 2 times negative 9.8 times 150. If I put all that in my calculator, 2500, and then plus 2 times negative 9.8 times 150, I get negative 440. Uh-oh, what did I do wrong? It's not negative 9.8. It's not negative 9.8. It's 2. See, I make mistakes too. And I've been doing this for over a decade. There's no such thing as getting to a point where you never make mistakes. The best you can do is just get better at catching mistakes. Okay, now let's try that again. 2500 plus 2 times 2 times 150 is 3100. There we go. So v1 squared equals 3100, which means v1 is approximately, if I take the square root of that, positive or negative square root. Well, the rocket gets launched upward and continues to accelerate upward, and this is the point where the engine gets cut off. So by this point, it has developed a lot of upward velocity. It should be headed up. So I would take the positive square root of 3100, which gives me about 55.68. If I round it, 55.677 rounds to 55.68 meters per second. Okay, let's fill that in. And now we can copy it over to here, which allows us to solve for our delta y2 now. So for delta y2, I think I'm going to go ahead and switch colors here. For delta y2, I've got, let's see, v1, v2, and a2. I guess I'm going to use the third equation again because I still don't know time for the second phase either. I didn't know time for the first phase, and I don't know it for the second phase. Third equation is usually the way to go when you don't want to go out of your way to calculate t first. So this time it's going to be v2 that is the next velocity, and v1 is considered the previous velocity. So v2 squared equals v1 squared plus 2 times acceleration 2 times delta y2. Okay, this acceleration is going to be negative 9.8. So v2 squared, that's just 0 squared, equals v1 squared. I could put 55.68 into my calculator and square it, or I could be more precise and say v1 squared is 3100. But that leaves out the rounding error So that's what I would prefer going with. Okay, and then plus 2 times negative 9.8 times delta y2. So that's going to be negative 19.6 delta y2. If I add 19.6 delta y2 to both sides, then I end up with 19.6 of delta y2 is equal to 3,100. And if I go ahead and divide both sides by 19.6, I get 158.16. Delta y2 is positive 158.16 meters. So actually not too far off from what I drew. I should have drawn delta y2 a little bit bigger if I wanted it to be to scale, but again, I did not know this ahead of time, so I cannot be held at fault for not drawing it to scale. Okay, that takes care of... No, wait, it doesn't. We're trying to calculate the maximum height. Delta y2 is just a step towards that. So maximum height is going to be from the ground all the way to here, so that's going to be delta y1 plus delta y2. 150 plus 158.16. The maximum height, I will write it up here, is equal to 308.16 meters. Okay, that's part A. Part B, what is the time it takes to reach the maximum height? So that's going to be the time it takes for phase 1 to start and end, and the time it takes for phase 2 to start and end. So we are looking for T1 plus T2, which means we now need to calculate T1 and T2. All right, should be pretty straightforward. You have two options. One option is to use the second equation of kinematics, which I do not recommend because it leads to having to solve a quadratic. Sometimes you can't avoid that. But generally, if you have to choose between using the first or the second equation to solve for time, the first equation of kinematics is usually the better one to go with. So that's what I'm going to use. So phase 1, we've got v1 equals v0 plus acceleration 1 times time 1. v1 is 55.68 equals v0, which is 50, plus acceleration is 2 times t1. Okay, and if I subtract 50 on both sides, I end up with 5.68, and if I divide by 2, then I am left with, well, let's subtract the 50 first. 5.68 equals 2t1, and then that leaves me with t1 is equal to 5.68 over 2 is 2.84. Is 2.84, and that should come out in seconds. 2.84 seconds. All right, let's do similar for phase 2. So for phase 2, we have 0 for, oh, well, let me write it out first. We've got v2 equals v1 plus acceleration of phase 2 times time of phase 2. That's going to be 0 equals 55.68 plus negative 9.8 times t2. Okay, so we've got a lot of starting velocity once gravity takes over. So gravity is going to need more time to slow this thing down. Slowing something down from 55.68 to 0 is generally going to take longer than it took to speed it up from 50 to 55.68. So I'm expecting T2 to be larger than T1. That's just a quick intuitive check that you could do just to kind of make predictions and make sure that your results are falling within your predictions. So anyway, subtract 55.68 on both sides, or add 9.8 T2 on both sides. Yeah, I think I would rather do that. That way I'm only dealing with positive numbers. 9.8 T2 equals 55.68. And divide by 9.8. 55.68 divided by 9.8 is 5.6816. I'll just round it to 5.68 seconds. T2 is equal to 5.68 seconds. Which means that the total time from launch to the maximum height, T rise as I call it, is equal to T1 plus T2, 2.84 plus 5.68. 2.84 plus 5.68 is about 8.52 seconds. 8.52 seconds. And that gives us our answer for part B. And then part C, what is the total time in the air? What is the hang time? For that, we need to find T3 and add it to T1 and T2. We've already added T1 and T2. We just did it, so we can take this 8.52 and add T3 to it, and then we're done. So in order to be able to do that, we need a third piece of information here. And which third piece of information do we have? It would be delta y3. We already know, we just calculated what the maximum height is going to be. So now we know exactly how much displacement occurs for phase 3 if you're starting from the maximum height and going back to the ground. Delta y3 is going to be all of this. So if I do 150 plus 158.16, my maximum height, 308.16 meters, then my delta y3 is 308.16 meters, right? Wrong. Remember the direction. Delta y3 is a downward displacement, and we're defining down as negative. If you did a version of the problem where you define down as positive, you do you, I guess, but I'm just going to stick with what's traditional and intuitive because that's what most students are probably going to do, and it's less confusing that way. Now that I have that, we can try and calculate T3. Do I have an equation that involves delta y, acceleration, the starting velocity of that phase, and time? That would be the second equation. Now, wait a minute, Al. You just told us to avoid using the second equation of kinematics, right? It results in a quadratic, you said. Well, not this time, because the second reason that splitting the phases of motion at the top over here is a good idea is because it gives you an initial velocity of 0 for one of your phases. And what that does for us is it simplifies the second equation of kinematics. If I do delta y3 equals v2 times t3 plus 1/2 acceleration 3 times 3 squared. Well, v2 is 0 here, so that's gone. That's a 0. And I don't have a quadratic equation anymore. I just have my time is going to be squared, and I have to do a little bit of algebra, but in the end, all I have to do is take a square root instead of using the quadratic formula. So, yeah, this is nice. This we can work with, which means we don't even need to calculate v3. But if we didn't have this shortcut and you were desperate to avoid using the second equation, you would just use, I guess, the third equation to calculate v3 and then the first equation to calculate t3. Anyway, if I go ahead and plug in my numbers, I've got negative 308.16 is equal to, that's a 0, and then 1/2 times negative 9.8 times t3 squared. These negative signs will cancel out, which is good because when you solve for t3 squared, it better come out positive. You can't square root a negative after all. We're not doing imaginary numbers in Physics 1 or Physics C, thankfully. You can deal with that when you're in college. If you didn't get these negatives to cancel out, that would be your clue that you did something wrong, and that something wrong would probably be that you forgot this negative sign over here. So yeah, if you find yourself taking the square root of a negative while doing free fall problems, go back and double check the directions of your displacements. That's probably what went wrong. And if not, then the next thing to check would be the directions of your velocities. Maybe you used the third equation of kinematics to solve for one of your velocities and you forgot to consider the negative square root as an option. Anyway, half of 9.8 is 4.9, so if I divide both sides by 4.9, 308.16 divided by 4.9 is 62.88979592. I'm not going to round that just yet. That's going to be equal to t3 squared, and if I take the square root of that number, then I get 7.93. I get t3 equals 7.93 seconds. And I actually should have, before even calculating this, I should have made a prediction. Just try to estimate how long would it take to go all the way down here. You would already know that from this point to this point, it would just take the same amount of time as it took from this point to this point. We do have symmetry from here to here after all, so you would know that it's at least 5.68 seconds for part of T3. And for the second part of T3, well, if you compare it to the first phase had an overall acceleration of 2, while the second phase has an overall acceleration of 9.8. So just comparing the accelerations, you would expect this last bit over here, to occur much quicker. Going up with an acceleration of 2 versus going down with an acceleration of 9.8 downward. Yeah, you would expect this stage to go by much faster. So you would expect the second part of T3 to be less than 2.84. So it does actually fit within predictions that T3 is less than the total time to rise is less than 8.52 seconds. That actually checks out. So now to calculate the total hang time is just the time to rise plus the time to fall being 7.93, 8.52 plus 7.93 is 16.45. I'm getting 16.45 seconds of travel in the air. And there we go. Now then, what do I want to do next? Which problem did I do after that? This one. And let's see if I can fit it in the bottom over here. So it says, an indestructible bullet 2 centimeters long is fired straight through a board that is 10 centimeters thick. The bullet strikes the board with a speed of 420 meters per second and emerges with a speed of 280 meters per second. Part A is asking, what is the average acceleration of the bullet through the board? Part B, what is the total time that the bullet is in contact with the board? And Part C, what thickness of board, calculated to the nearest tenth of a centimeter, would it take to stop the bullet, assuming that the acceleration through all boards is the same? So let's draw the situation first, and let me make sure that's all within frame. That's something you always have to be careful about something I always have to be careful about when doing things towards the bottom of the page. Okay, so we will say that this is 10 centimeters. Let me work that out in this light blue. So that is 10 centimeters. And then we have a bullet that is 2 centimeters long. A bullet that is 2 centimeters long. And it says it enters with a velocity of 420 meters per second. So I'm going to call that V initial. V initial equals 420 meters per second. And it emerges with V final equals 280 meters per second. And we know how bullets work. The direction of V final must be the same as the direction of V initial. There's no scenario where you fire a bullet into a block of wood and it comes out facing the opposite direction. That just defies common sense. So both the initial and final velocities here have the same direction. I'm going to call that the positive direction for this problem. And then what did it say? First, what is the average acceleration of the bullet through the board? It's going to be quite the number, because we're talking about a bullet here. This all happens really, really fast. I mean, if it slowed down from 420 to 280, then its whole time inside this board, it was moving at least 280 meters per second. And how much time traveling at 280 meters per second would it take to go through 10 centimeters of board? Not a whole lot of time. So this is a very, very big acceleration happening over a very, very short period of time. But before we can solve that, we need to take the length of the bullet into consideration. So the bullet enters over here with its tip first making contact with the board, and it is considered as being decelerated by the board all the way up until the back of the bullet emerges from the board. If you miss this, you are going to ruin the whole problem for yourself. Deceleration starts when the tip of the bullet touches the front side of the board and ends when the back side of the bullet is in contact with the opposite side of the board. So the actual displacement, I can either think of it as the displacement of the tip of the bullet, or I can think of it as the displacement of the back of the bullet. It doesn't really matter which you go with, but either tip to tip or back to back. I'm just going to do from when the tip of the bullet enters to where the tip of the bullet is at the moment it loses contact with the board. That is the total displacement. That is your delta x of the bullet. I know I drew it a bit crooked, but I think you understand what I mean here. So our delta x is not 10 centimeters, but 12 centimeters. Our delta x is equal to 12 centimeters. So that's the biggest issue with this problem. Once you have this figured out, once you understand this, the rest is easy enough. It's just that the numbers are a bit weird and unusual. It's not really what you're used to seeing in most problems. But yeah, let's go through it. So first off, we need to convert our units. I've got meters per second and meters per second, and my displacement is in centimeters. I say convert displacement from centimeters to meters rather than converting both of my velocities to centimeters. I think that would be the better play here. So I'm going to say delta x equals 12 centimeters. Every 100 centimeters is equal to 1 meter. Centimeters cancel with centimeters there, and 12 over 100 is just 0.12. 0.12 in meters. So our displacement is 0.12 meters, and we know V initial and V final. So along with delta x, that's 3 pieces of kinematic information. We can calculate the other 2. We can calculate acceleration, and we can calculate time. We were asked only for acceleration, so we can skip calculating time, which means we can skip the first equation, and the second equation we can jump straight to the third. So the third equation says V final squared equals V initial squared plus 2 times the acceleration times the displacement. So that's gonna be 280 squared equals 420 squared plus 2 times, we don't know the acceleration yet, times 0.12 for the displacement. Okay, 280 squared. I'm going to go ahead and subtract 420 squared from it. And that's negative 98,000. So I'm getting negative 98,000 equals 2 times A times 0.12. That's going to be 0.24 times A. And divide by 0.24, and yes, this number is about to get even bigger. Negative 98,000 divided by 0.24 is quite the number. I guess it might be better to express it in scientific notation, but our acceleration is equal to negative 408,333.33 meters per second squared. And yeah, the threes just keep repeating from there. So if you want to rewrite it as a fraction, negative 408,333 and a third, then be my guest. But that's acceleration. That's part A. Part B. What is the total time that the bullet is in contact with the board? Okay, now we have to calculate time. That shouldn't be too hard. Now that we have the acceleration, it would be easier to use the first equation to solve for time. If you try to do it using the second equation, God help you with your quadratic formula. Yes, there will be times when it's needed, but not today. It is unnecessary to do the quadratic formula here. We can just use the first equation of kinematics. So pick the easy option, save yourself time and grief and frustration. V final equals V initial plus AT. That's gonna be 240, wait, no, not 240, 280 equals, now I have to double check all my other work. Did I accidentally write 240 anywhere? It doesn't look like it. 280 equals 420 plus, well, that. I'm just going to write it as A because I don't want to write that whole number again, times T. And then 280 minus 420 is negative 140. So we've got negative 140 equals A times T. Negative 140 divided by A. Negative 140 divided by this number. Fortunately, I still have it on my calculator, so I can just copy-paste it without having to write the whole number again. And I'm getting 0.000342857. I'm getting T is equal to well, I'm gonna, actually, no, I'm not. I'm just gonna write it as is, 0.000. Let's take 3 digits. 3428 becomes 343 seconds. Yeah, I think 3 sig figs is good enough for this one. So yeah, very, very, very tiny amount of time. Massive acceleration, yes, but over a very, very small amount of time results in not a very big decrease in velocity. Well, I guess a decrease from 420 to 280, a decrease of 140 might be considered big compared to the velocities we've seen in other problems before this one, but in the grand scheme of things, relative to this acceleration, if this acceleration had gone on for a full second, if it had gone on for just under a minute, we would already be talking about decelerating something from like light speed to 0. If somebody wants to do the math and calculate how long it would take for an object at light speed to slow down at this rate of acceleration, then be my guest. You can look up the speed of light on Google if you don't happen to know it, or you can probably find it in the front or back cover of your physics textbook. Anyway, part C. What thickness of board, calculated to the nearest tenth of a centimeter, would it take to stop the bullet, assuming that the acceleration through all boards is the same? How thick would the board have to be? I guess I'm going to call the thickness L. L for length. So for what L, rounded to the nearest tenth of a centimeter, would the board have to be in order to completely stop the bullet? Well, for that, we need to first figure out what delta X is needed to stop the bullet. And that shouldn't be too hard to do. We can just use the third equation of kinematics again, but this time for V final, instead of 280, we're just going to plug in 0, and this time delta X is going to be the unknown. So let's go ahead and do that. And leverage the last remaining bits of this page before I have to flip it over. So we've got 0 equals whatever 420 squared was. 176,400 apparently. 176,400, that's what I get from squaring the 420, plus 2 times, we know the acceleration now, I'm just going to write A because I don't want to write that long number again. And what is this? I'll call it delta X stop. What is the amount of displacement needed to stop the bullet? Okay, so I can subtract 176,400 on both sides and then do negative 176,400 divided by parentheses 2 times that mess. Let me see if it's still in my calculator memory so I can copy it over. Yes, it is. Close parentheses, and I'm getting 0.216. I'm getting delta X stop is equal to 0.216 meters, or 21.6 in centimeters. That's in centimeters to the nearest tenth, so we're done, right? Wrong. The question was not asking what displacement the bullet will have in order for it to stop. The question was, what thickness of board do we need? Delta X is the thickness of the board plus the length of the bullet. So we need to subtract 2 centimeters from this. The L that we need, L for stopping the bullet, L required for stopping the bullet is 21.6 minus the 2 centimeters. That's going to be 19.6 centimeters. And there we go. It's easy to underestimate a problem like this. When you first read it, you think, oh, it's simple. I'm just given 2 velocities and some distances. Oh, this is going to be super easy. But then you read the details and you draw an accurate picture and you realize there's more to it than you think. Okay, next problem. 2 objects in free fall. We haven't done these yet. So 2 objects in free fall. A ball is thrown upward from the ground with an initial speed of 25 meters per second. At the same instant, another ball is dropped from a building 15 meters high. After how long will the balls be at the same height? So one ball, I'm going to call it ball A, is thrown upward I'm going to call this VA initial is equal to, what did it say? 25 meters per second. 25 meters per second. I probably should have written it somewhere lower, but it's okay. At the same instant, another ball is dropped from a building 15 meters high. After how long will the balls be at the same height? So we've got, I guess that'll be my ground level, and then that's going to be my 15 meters. And here's my second ball. I'm going to call it ball B. It's dropped from 15 meters high. They didn't say it was thrown up from 15 meters high, nor did they say it was thrown down from 15 meters high. They simply said it was dropped, and we can reasonably assume it was dropped by a person whose hand was at 0 meters per second at the moment of the drop. In other words, we can assume that the second ball was dropped from rest. Otherwise, this problem would be unsolvable. So VB initial is going to be 0. After how long will the balls be at the same height? So ball A is going to go up, reach some sort of maximum height, and then come back down. Let me think about this. Would the maximum height of ball A be greater than 15? Well, at 25 meters per second, that gives you a little more than 2.5 seconds for gravity to stop it. Gravity would need a little more than 2.5 seconds to bring it to a stop. And the average velocity between when it's first thrown to when it reaches its peak, since it's under constant acceleration, that average velocity would just be half of 25 plus the velocity at the top, 0. So 25 plus 0 over 2 would be 12.5. And if I did 12.5 times about 2.5 seconds, that's already way more than 15 meters. Yeah. Okay, so ball A in its rising phase is definitely going to rise well above 15 meters, which means that ball A is going to be at the same height as ball B while it's still on its way up, before it ever reaches its maximum height. And then we can draw the trajectory of ball A continues upward for some time, and eventually it comes back down and lands on the ground. Ball B, on the other hand, let me use a different color for it. Ball B is just going to go straight down like that. Okay, so at some point, we're going to reach a point where ball A has achieved a displacement of delta YA, and ball B has achieved a displacement of delta YB, and their positions at that specific moment will be the same. So whatever this is, we can call it H final. This is going to be H final, or you could also call it Y final if you wanted, but I'm going to go with H final. This H final is what we're trying to calculate. And also, we are trying to calculate, that's the first thing we need to calculate, and then once we have it, we then reuse it to calculate the actual question they're asking, which is how much time? how much time does it take for these two balls to reach this height? Okay, let's go ahead and write down what we can put together. I see that the displacements of both objects are involved. And since we're dealing with two moving objects, we have to decide how are our stopwatches going to work. Are we going to assign separate times to each of these objects, a TA and a TB, or would we rather have the stopwatch being held by a third person who's observing both objects in motion and tracking time according to their own perspective? In this case, since both objects start moving at the exact same time and every change in their position and motion is all occurring in the same amount of time, I would just go for a single shared timer for both of them. I would just use a shared timer. Actually, let me illustrate what I'm even talking about with stopwatches in case some viewers have never actually heard of a stopwatch. Maybe English isn't your first language. Let me open the little timer thing. Yeah, over here. So here's a stopwatch, and if I run it, I can do, let's see, yeah, I can do like splits. Okay, so you see that the timer just keeps on running like that, so that's what I would call a split timer. Okay, I've got the split times on the right, and then I've got the individual durations between the splits on the left. Okay, nice. I've never actually used this on my phone for anything before, but yeah, when I'm talking about stopwatches, I'm asking if I were to assign a stopwatch to each of these objects, would their readings be the same, or do I want them to start and stop their stopwatches differently? That's the decision that you have to make every time you're dealing with a problem that has more than one object in motion. Anyway, I'm going to clear that and put this phone away. Let me see. And I lost my train of thought. That took me out of it. Give me a minute and let me gather my bearings here. So in this case, since the motion of both objects starts and ends, I'm considering the end to be when they reach here. Since both of them start and end their tracked motion at the same times, a single stopwatch for both of them is all we need. So I'm going to say that the time for A, if I did give both of them their own individual stopwatches, it would be a waste because they would just be reading the same thing. Both of them would push start at the same time and push end at the same time. So I'm just going to call it T. Okay, so now we've defined our time, and we want to probably use the second equation of kinematics, since that involves both time and displacement. The third equation of kinematics involves displacement, but it also involves final velocity, and we have no clue how the final velocities of these two objects are going to be related, if at all. So yeah, second equation is probably the way to go. So delta YA is going to be VA initial, forgot the comma, times t plus 1/2 the acceleration times t squared, and delta yb is going to be defined similarly. Delta yb is going to be vb initial times t plus 1/2 the acceleration times t squared. The acceleration, of course, is negative 9.8. We're assuming this is occurring on planet Earth near its surface, so 9.8 is a pretty reasonable assumption for the magnitude of our acceleration. And we also want to figure out how delta YA and delta YB are related to this H final. So delta YA is the difference from the final position, which is going to be here for our purposes, and the initial position, which is here. This initial position I'd be just marking as 0, so delta YA is equal to H final minus 0. Meanwhile, delta YB is going to be the ending position, which is also H final, minus the starting position, which is at a height of 15. Delta YB is going to be whatever H final is minus 15. And since H final is definitely somewhere lower than 15, this is going to be a negative number, which is consistent with my diagram. Delta YB is in the downward direction. Okay, so putting all that together, let's see what we can do. Let's plug in the numbers that we have. Oh, wait, no. Refrain from using orange until further down the page. Let's see, so delta YA and delta YB. Well, delta YA is just equal to H final, so I guess I could just do, over here, I can replace H final with delta YA. So delta YB equals delta YA minus 15. Yeah, there we go. And then delta YB is going to be VB initial times T, VB initial being 0, plus 1/2 the acceleration times T squared, equals delta YA minus 15. Delta YA, VA initial times T, so that's 25T, plus 1/2 A T squared, and then that's your delta YA, and then the minus 15. I don't actually need those parentheses, but for the sake of organization, I decided to include them. Now, the interesting thing here is that the 1/2 AT squared cancels on both sides. That's why I didn't even bother writing in the negative 9.8. It cancels out. So that leaves us with 0 on the left-hand side equals 25T minus 15. Add 15 to both sides. 15 equals 25T. T equals 15 over 25. Reduced by 5, that becomes 3 over 5. So T is equal to 3/5 equals 0.6 seconds. T is equal to 0.6 seconds. That's not the actual question. Our actual question is what is H final, but now that we know T is 0.6 seconds, we can solve for H final using either this or this. I would rather use this because it's simpler. So, well, actually, let me think. Which one would be simpler? It doesn't matter. They should both be the same thing anyway. I'll just solve for delta YA. So H final equals delta YA equals VA initial was 25 times T is 0.6 plus 1/2 the acceleration times the time squared. And if I plug all that in, 25 times 0.6 minus 4.9 times 0.6 squared. Syntax error. Oh, minus. I hit the negative button. Okay, 13.236. I'm getting 13.236 meters. And I would leave it at that and maybe come back to it later after I've answered all the other questions if I was doing this on a test. But if you're just doing practice exercises at home, then it would be worthwhile to just double check and see if using the other method gets you the same result. So let's do that real quick and see. Delta YB equals H final minus 15. So if I go delta YB, what was it again? It was 0t plus 1/2 AT squared. So 0 plus 1/2 negative 9.8, getting ahead of myself, negative 9.8 times 0.6 squared equals H final minus 15. That's negative 4.9 times 0.6 squared, and then add the 15. Negative 4.9, negative 4.9 times 0.6 squared, and then plus 15. And I do indeed get H final equals 13.236 again. I do indeed get H final equals 13.236 meters. Often a good idea to spare the extra few minutes to check if two things that should lead to the same result actually do lead to the same result. Helps you develop intuition and confidence when practicing. Maybe don't do this during your exam when you're pressed for time, but make sure to do it well before, when you actually do have the time, so that you can actually learn from it before the big test day. All right, next question is do I want to do, let's see, that would be a two-phase problem. Now we can skip that one. Okay, how about this one? Two students are on a balcony 19.6 meters above the street. One student throws a ball vertically downward at 14.7 meters per second. At the same instant, the other student throws a ball vertically upward at the same speed. The second ball just misses the balcony on the way down. What is the difference in the two balls' time in the air? And what is the velocity of each ball as it strikes the ground? And how far apart are the balls 0.8 seconds after they are thrown? So we have, they start from 19.6 meters high. I see something in these numbers. They very clearly intended for you to use 9.8 for G and not 10 here. And You can probably see that if you used 9.8 a lot, you would recognize numbers like 19.6 and 14.7. 19.6 is just 2 times g, which you encounter a lot when using the third equation of kinematics, right? Plus 2 times the acceleration times delta x is the end of that equation. So multiplying 9.8 by 2 and getting 19.6 is a common occurrence if you've practiced with it a lot. Similarly, sometimes you multiply 9.8 by 1.5, which would get you 14.7. So some very interesting numbers that they've picked here. That's the first thing that stands out to me. The untrained eye would probably miss it. But yeah, if you're used to using 10 for G, not for this problem. For this one, use 9.8. They very clearly intended for it to be 9.8 for this problem. Anyway, drawing. So we have starting height 19.6 meters. Starting height 19.6 meters. 2 balls, I'm going to call them A and B. One of them is thrown straight down at a speed of 14.7. Speed is just the magnitude. It does not tell us the direction. 14.7 meters per second is the speed. The velocity is going to be negative 14.7 if you stick with the convention that down is negative. The second one is thrown up with a speed of 14.7 meters per second. So I'm going to go ahead and write VA initial is negative 14.7 meters per second, while VB initial is positive 14.7 meters per second. All right. What else does this problem tell us? So they were thrown at the same instant. The second ball just misses the balcony on the way down. Okay, so they're both thrown, and the one thrown straight up comes back down, but instead of landing on the balcony, it actually just continues to fall to the ground. So here's our ground level, and this one just goes straight down to the ground. Okay, where were we? Part A, what's the difference in the 2 balls' time in the air? What is the difference in their hang time? So here, we can take advantage of some of the things that we learned last time about symmetry. Of course, you could also just do things the hard way, but taking advantage of symmetry, I know that for this second ball, by the time it rises and then comes back down to here, I know 2 things. One, I know that the time it took to rise up from where it started to its maximum height equals the time it took to fall back down to its initial height. The second thing I know is that when it gets back down here, it's going to have a downward velocity of 14.7 meters per second, which means the rest of this downward part of its trip from balcony height to the ground is going to be identical to the trip that ball A goes through. Same velocity at this height. It's dropping by the same amount. It's dropping 19.6 meters, and it's dropping under the same acceleration as ball A from this point onward, which means the same amount of time should pass from here. So the amount of time from here, what am I doing? Curly bracket. The amount of time from here to here should be equal to the amount of time from here to here. These two times should be equal. So if I'm being asked what is the difference in their times in the air, I can just cancel this out, and the difference is just going to be the amount of time that ball B is rising plus the time it comes back down to its initial height. I can just calculate the time it takes to go up and then back down to a 19.6 meter height, and I can just ignore what happens afterward because that time is going to be the same as it was for ball A, and I want just the difference. The difference is that ball B spends time rising. Everything else is identical after that point. So, did I say rising? Well, rising and falling back to its initial height is what I meant to say. So yeah, we can calculate the amount of time it takes to do this part of the trip. And because of symmetry, I only have to calculate 1/2 of it and then just multiply by 2. I'm going to calculate the amount of time it takes to move from to go from a velocity of 14.7 meters per second upward to 0 at the top. That's what I want to calculate. And for that, I can use the first equation of kinematics, because I know V at the top, V top, is equal to 0, and we already have VB initial, so that's two velocities. Acceleration I already know is negative 9.8. That's 3 pieces of information I can calculate with that. So first equation of kinematics would be the way to go here. The second velocity would be V top equals the first velocity would be VB initial plus the acceleration times, I guess I'm going to call this TB rise, the amount of time it takes ball B to rise to its maximum height before it starts falling back down. So that's going to be 0 equals 14.7 plus negative 9.8, so minus 9.8 TB rise. Add 9.8 TB rise to both sides, divide by 9.8. 14.7 over 9.8 is exactly 1.5. The time for ball B to rise to its maximum height is equal to 1.5 seconds. So it takes 1.5 seconds to go from here to here, which means it would also take another 1.5 seconds to go from here to here. So the total time that ball B spends traveling in the air that ball A doesn't spend, the total difference in their time is that ball B is going to take 3 seconds longer in the air compared to ball A. So TB hang, total hang time of ball B, minus total hang time of ball A is just going to equal 2 times TB rise, is going to equal 2 times 1.5 equals 3 seconds. Ball B spends 3 extra seconds in the air before making contact with the ground. Okay, part B. What is the velocity of each ball as it strikes the ground? Well, Because of symmetry, we only have to do one calculation here. If you start with 14.7 meters per second downward and you drop 19.6 meters, you're going to reach some sort of final velocity here. Ball B is going to move down. It's going to move up in the air, and then it's going to come back down to here, and then it's going to have a downward velocity of 14.7 from this point onward. So it should follow the same path. It should end up with the same final velocity. I think I might have someone at my door. Let me double check.
Can I spray a bit?
Yeah.
Just want to get around your kitchen really quick. So.
Yeah, don't mind me. I'm just recording a lesson, so
Well,
if you hear me talking.
When I came in, I figured you're working in your office.
Yeah.
You got it. Thank you.
All right, where were we? Oh, right, we were trying to calculate the final velocity of each of the balls. It's going to be the exact same thing for both of them. We already explained why that is, so let's go ahead and actually calculate it. So we're going to do, let's see, we have an initial velocity, we need a final velocity, and we've got a displacement of 19.6 meters downward. So we're going to do third equation for this. We're going to do, it doesn't matter which ball we pick, I'll just pick ball A. So VA final squared equals VA initial squared plus 2 times our acceleration. Let me make that 2 a little bit clearer. Times delta y. We don't know this yet. VA initial squared. It was negative 14.7, but if we're going to square it, I guess the negative doesn't really matter. And then plus, we've got 2 times, our acceleration is negative 9.8. And our displacement is, be careful about this, we're going down, not up. We're going down 19.6 meters. So it's going to be negative 19.6 for our displacement. And putting all that together, what does our calculator give us? 14.7 squared plus, well, these negatives cancel, so 14.7 squared plus 2 times 9.8 times 19.6 is 600.25. And if I take the square root of that, is that going to be a nice round number? Yes, it is. I'm getting 24.5. So VA final squared is equal to 600.25. And then if I take the square root, I get 24.5 meters per second. Or do I? What is wrong with this? If you've been paying attention for most of this recording, then I think you've picked up on my pattern. It's the negative sign. Don't forget the negative sign. We're taking the negative square root here because the final velocity of ball A is going to be a downward velocity. And of course, I should also write this is equal to VB final as well. And that completely answers our question. Oh, no, not yet. There's a part C. How far apart are the balls 0.8 seconds after they are thrown? So we are assuming here that at 0.8 seconds, ball A has not yet landed on the ground. Otherwise, that complicates things. So let me see, the amount of time it would take ball A to land. How much time would that be? Well, now that we know VA final, we can calculate that pretty easily. You don't really need to do it for this problem if you trust the author of the problem to have already accounted for that. But if you're going to become a professional physicist, you might want to get in the habit of double checking these sorts of things just to make sure that everything is above board, so to speak. So let's do that calculation real quick. If I do VA final equals VA initial plus acceleration times time, how much time does it take ball A to fall? Negative 24.5 equals negative 14.7 plus negative 9.8t, so minus 9.8t. Do negative 24.5, add 14.7 to both sides. That leaves me with negative 9.8 equals negative 9.8t. And that means t is equal to 1. So ball A takes a full 1 second to hit the ground, which means for what they asked us in 0.8 seconds, ball A has not yet reached the ground, so we don't have to worry about complications due to the ball bouncing. Not that you would have enough information to handle such complications anyway. So yeah, how far apart are they 0.8 seconds after they're thrown? Calculate delta YA and delta YB and figure out what the difference is. So where do I want to do this? Yeah, let's start this on a new sheet. Can I? Well, I don't want to have to redraw the same. Okay, fine, we'll redraw it. So they both start at 19.6 meters high. And ball A is going to travel some displacement delta YA that is not quite 19.6 meters downward. So that's delta YA. While ball B is going to spend, let's see, it spends 3 seconds above the initial 19.6 meter height, which actually means then that it would still be on its way up at 0.8 seconds. So at 0.8 seconds, it takes 1.5 seconds to reach its maximum height. So in 0.8 seconds, it would still be on its way up. So delta YB would be this, somewhere around here. Actually, probably somewhere lower, but I wanted to make it longer so that it's actually visible on my diagram. If I drew it too short, it would have been unclear. I decided to sacrifice accuracy in the name of clarity. Okay, so the question was, how far apart are they? If that's ground level, let me actually draw a solid line for that. If that's ground level, how far apart are they? That is, what is this distance? What is this distance? So we are going to do, let's see, delta YB is positive, delta YA is negative. So if I want to calculate D, I guess I'm going to have to do delta YB minus delta YA. Right? This positive minus this negative, that would result in adding their magnitudes. Or if you don't like that logic, you can say D is equal to magnitude of delta YA plus magnitude of delta YB. Magnitude of delta YA is just going to be the negative of delta YA since it's a negative to begin with. And delta YB, its magnitude is just delta YB itself because it's already positive. It doesn't need to be negated. So now that we have that, just use the second equation of kinematics and you should be good to go. Second equation of kinematics for A, we've got delta YA is equal to V initial negative 14.7 times t 0.8 seconds plus 1/2 acceleration times t squared. And delta YB will be defined similarly. Delta YB, it starts with positive 14.7 for its initial velocity, and then for 0.8 seconds, and then everything else is the same between the two balls. Okay, and if I'm doing negative delta YA plus delta YB, then I can do this bottom equation minus this top equation, which means I can take a shortcut. If I'm doing this minus this, then these cancel out. The second term cancels out, and I'm left with 14.7 times 0.8 minus negative 14.7 times 0.8. I'm getting 14.7 times 0.8 minus negative 14.7 times 0.8. I guess I wrote that in the wrong order. This is the minus delta YA part. I wrote it on the right hand side, and then the plus delta YB is over here on the left, and I forgot an opening parenthesis there. Okay, so factor out the 0.8, and actually this double minus becomes a plus, so I would just have 2 times 14.7 times 0.8. 2 times 14.7 times 0.8 is 23.52. .52 meters of separation between the balls at time 0.8 seconds since their release. Now, come to think of it, I did not even discuss my timers and stopwatches for this problem. I should have done that, but I guess you already figured out from how I solved this that yet again we used a shared timer. All right, what do we have next? We've been going for almost 2 hours, and I can go up to 3 today. I know what I want my last problem to be. And I think I definitely want to include at least one of these two. Okay, let's do this one next. So it says, a young woman named Kathy Cool, Cool is spelled with a K, buys a sports car that can accelerate at the rate of 4.9 meters per second squared. She decides to test the car by drag racing with another speedster, Stan Speedy. Both start from rest, but experienced Stan leaves the starting line 1 second before Kathy. If Stan moves with a constant acceleration of 3.5 meters per second squared, and Kathy maintains an acceleration of 4.9 meters per second squared, find A, the time it takes Kathy to overtake Stan, and B, the distance she travels before she catches him, and C, the speeds of both cars at the instant she overtakes him. So here we've got ourselves another racing problem. Okay, so I'm going to draw two cars. Car K will be Kathy's car, and car S will be Stan's car. I feel like I've made these cars way too lopsided, but that's okay. I'm not the art teacher after all. The best art I can do is pixel art, and I'm out of practice with that. I need to get back onto that at some point, but time is not as abundant as it was when I first started that stuff. Where were we? So they both start from rest. Let's see, how do I want to assign stopwatches this time? So this time, I want to do separate timers this time. Yeah, I think that would be for the better. I'm going to have it so that each one of them has a separate stopwatch assigned to them. I want their times to be separate because one of them is not moving for a second while the other one is. So I think it would be more convenient to track their time separately. So Stan gets a head start for 1 second. And then from that point on, it's smooth sailing until the point where Kathy catches up to him. And Kathy starts a second later. And because she has more acceleration, she eventually does catch up to him, assuming air resistance doesn't cap her speed out. Which is a reasonable assumption. Well, actually, it's not a reasonable assumption, but it's the only assumption we can make because we don't know how to work with air resistance. At least not at this point. And for the Physics 1 students, you will only learn how to deal with air resistance in the most extreme and simple of situations. You're not going to have to do calculus to figure out how air resistance changes things in real time. That's for the Physics C students. Okay, which color do I want to use next? Man, decisions. I want to go ahead and write down their accelerations. So Kathy has an acceleration of, it said 4.9. Acceleration of Kathy is 4.9. I'm going to say this is in the positive direction. I'm going to I'm going to just assign positive to the direction that they both move. Neither of them has a reason to move in reverse. They're in a race. They're both just going to move forward if they're moving on a straight track. And then the acceleration of Stan is going to be positive 3.5 meters per second squared. So find the time it takes Kathy to overtake Stan. So I'm going to call that time, whatever this is, I'm going to call it Kathy's time. Stan's time is going to include this extra 1 second. So this over here occurs during the time that Kathy is in motion, and then Stan's time is the whole thing, including this extra 1 second. So I'm going to go ahead and state that Stan's clock is going to read 1 second more than Kathy's clock. Or stopwatch, rather. Saying clock implies that this is a relativity question, and we're not touching that. We're not touching that with a 10-foot pole. Save that for AP Physics 2. Or college, as the case may be. As for their velocities, they would have to start from rest. So V Kathy initial equals 0, and V Stan initial is also going to be 0. And I think that's all we need. Let's get started with solving. So what do I want to do here? I know their accelerations. I don't know either of their times, but I know that their times are connected. I know their initial velocities. Let's go ahead and write their displacement equations. Let's go ahead and write their delta x equations. So they should both achieve the same delta x, right? They should both have the same delta x. Delta x Stan equals delta x Kathy. I'll just call it delta x in general. So I can start with this. I can start from the fact that their delta x's are equal and see if I can do something with this relationship between their times. A relationship between their displacements plus a relationship between their times should make up for my lack of a third kinematic value for either of them. If I combine those two pieces of information together, delta x Stan equals delta x Kathy. Delta x for Stan would be V Stan initial. That should be a comma, not a period. V Stan initial times T Stan plus 1/2 of his acceleration times his time squared equals delta x of Kathy. That should be V Kathy initial times her time of movement plus 1/2 of her acceleration times her time squared. V Stan initial is 0, so that's gone. V Kathy initial is also 0, so that's gone. That makes things easier for us. That means I can cancel the 1/2 on both sides, and I'm left with 3.5 T Stan squared equals 4.9 T Kathy squared. I can go ahead and replace Stan's time with Kathy's time plus 1. Oh boy, here it is, the unavoidable quadratic. 3.5 times t Kathy plus 1 squared equals 4.9 t Kathy squared. If I FOIL this, I'm going to also divide the 3.5 and get it out of the way. If I FOIL this, then I get t Kathy squared plus 2t Kathy plus 1 equals 4.9 over 3.5 t Kathy squared. Okay, I'm going to subtract everything from the left-hand side over to the right, so that leaves me with 0 equals, let's see, subtracting 1 tk squared, so that would be 4.9 over 3.5 minus 1 all times tk squared. I don't want to plug things in just yet. And then minus 2 tk, and subtracting the 1 would be minus 1. Yeah, okay, I don't see anything that would cancel out or simplify if I left this as is. Okay, let's actually put it in the calculator then. So 4.9 over 3.5 is 1.4, and then minus 1 is 0.4, so that's going to be a 0.4 over here. Equals 0.4 tk squared minus 2 tk minus 1. Yeah, this we're not going to be able to just factor. We have to use the quadratic formula. We have to use the quadratic formula for this. So, negative b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully you got all that. I'm sure you've heard it 100 times. So, negative of negative 2 plus or minus the square root of negative 2 squared plus 4 times a is going to be 0.4. Wait, no, not plus, minus. But it's going to turn into a plus anyway because that's a negative 1. So yeah, it would have been minus and then negative 1, but the negatives cancel, leaving us with a plus. There we go, fixed it. Oh goodness, why is orange dying on me? It's still full of ink. Over 2 times a, 2 times 0.4. Okay, let's see what we get. So tk equals, if I put this into my calculator, negative 2 is positive 2. I'm going to start with plus the square root, and then negative 2 squared is 4, and then plus 4 times 0.4 times 1, all over 0.8. In the plus case, I get 5.458. And if I copy paste it and change the plus into a minus there, in the minus case I get negative 0.458. So clearly the negative answer for us is nonsense, but if you were to plug it in, I think what you would get is how far they would have to travel if they each traveled backwards starting from the time that Kathy actually moved. So Stan would have already moved here for 1 second, and then if you assume they accelerate backwards from that point for 0.458 seconds. I haven't done it in a while, so I don't exactly know what needs to be flipped and what doesn't. But I do know that if you were to plug in this negative time, you would get something that kind of does make sense in a world where time could flow backwards. You just have to be careful about what needs to be reversed. Anyway, we got the positive answer was 5.458, so let's go with that. 5.458 seconds. And that is Kathy's time. That is time since Kathy started moving. Is that what they wanted? The time it takes Kathy to overtake Stan. Yes, we wanted Kathy's time, so 5.458 is correct. If instead they had asked for the time since Stan moved, we would have to add 1 second to that. So be careful when solving these kinds of questions. Make sure you know whose time the question is asking about before you submit your final answer. Part B, the distance that Kathy travels before she catches Stan. So what is delta x? Well, now that we have TK, that should be easy enough to do. I'm going to use, which version of delta x do I want to use? I think I'll just use Kathy's version so that I don't have to do the plus 1 second. So Kathy's delta x was v Kathy initial plus t Kathy, that's a 0, plus 1/2 her acceleration times her time squared. So delta x is going to equal just 1/2 times 4.9 times 5.458 squared, and that's half times 4.9 times 5.458 squared is 72.98 meters. 72.98 meters. So that's part B. And then part C, what are the speeds of both cars at the instant she overtakes him? So for that, we would just use the first equation of kinematics. I think that one is easy enough that you guys could do it on your own. I don't think you need to see me doing that type of calculation anymore. But I'll set it up at the very least. So we would do for each person, let's say for Stan, for example, I would do V Stan final equals V Stan initial, which is just 0. They both started from rest. That's a reasonable assumption. Plus Stan's acceleration times Stan's time. So you would just have to add 1 to the 5.458 in Stan's case. And you would do similar for Kathy, except you don't need to add the plus 1 to the time. And you can calculate their speeds. And of course, prediction would be, and not just prediction, it would have to be that Kathy's speed is greater than Stan's speed. If you don't get that, then you did something wrong, because there's no way, if Stan has the lead, there's no way for Kathy to catch up to him unless she's moving faster than him. If Stan is the one moving faster, then the gap between them is growing, not shrinking. That wouldn't work. At the moment that a car from behind passes a car that used to be in front of it, the car that's passing from behind has to be moving faster than the one in front. That's just common sense. But yeah, I will leave the rest to you guys, I think that's an easy enough calculation at this point that you can do it. Okay, this next one has an interesting twist that most students don't see coming. So it says, it starts off actually quite simple. An ice sled powered by a rocket engine starts from rest on a large frozen lake and accelerates at 40 feet per second squared. So now we're working with feet instead of meters, but that's not going to be too much trouble for us. After some time t1, the rocket engine is shut down and the sled moves with constant velocity v for a time t2. If the total distance traveled by the sled is 17,500 feet and the total time is 90 seconds, find, for part A, the times t1 and t2, and then for part B, the velocity v. And then it adds more to the problem. It says at the 17,500 foot mark, the sled begins to accelerate at negative 20 feet per second squared. So part C, what is the final position of the sled when it comes to rest? And then part D, how long does it take to come to rest? Let me get a sip of water before I start this one. All right. So let's go ahead and draw the situation. So we've got a rocket-powered sled. Some people hear the word rocket and immediately assume vertical, but it's a sled. So we've got a rocket-powered sled. That travels with an acceleration. It starts from rest and travels for some time t1. Travels for some duration of time. That's a very bad looking curly bracket. Travels for some amount of time t1 under an acceleration. I'll call it acceleration 1 is positive 40 feet per second squared. Since everything else is in feet, this is not a problem. We don't have to make any conversions. Okay, after some time t1, the rocket engine is shut down, and I guess I should say over here, v0 is equal to 0, and whatever velocity it has at this point, I'm going to call that v1. Let's see, so after some time t1, the rocket engine is shut down and the sled moves with a constant velocity v, so whatever v1 is, they're calling it v for a time t2. For a time t2. And I don't know how long this time is, and I don't know how these distances are going to compare, so I guess this is not going to be drawn to scale. This is probably going to end up looking terrible once we figure out what the actual numbers are, but I'm just going to base my scaling off of mostly how much room I have left on this page. So that's t2 under a constant velocity v. That means that the acceleration for phase 2 here is going to be 0. If the total distance traveled by the sled is 17,500 feet, if the total distance, I guess I'm going to use, let's use pink for this. If this total distance d is equal to 17,500 feet, and the total time is 90 seconds, so I guess total time is 90 seconds equals t1 plus t2. And I guess over here I should also write this is equal to delta x1 and delta x2. So this is going to be delta x1, that's going to be delta x2, and this is going to be the sum of both of them. They're both already in the positive direction. I'm going to use right as my positive direction for this problem. So yeah, delta x1 plus delta x2 equals 17,500, and t1 plus t2 equals 90. So if that is the case, find t1 and t2 and also find the velocity v. So part A, find t1 and t2. And then part B, find v. And then I probably should not have written that over there because I just remembered I need that space for the third phase. Poor planning on my part. So for part C, it says, at the 17,500 foot mark, the sled begins to accelerate at negative 20 feet per second squared. So go back to this pen, and we're going to have, I guess, a delta x3 over here. And we're going to have acceleration 3 is equal to negative 20 feet per second squared. Let me wall those off from each other so that they don't look like they're part of the same thing. And it says for part C, what is the final position of the sled when it comes to rest? So I guess I'll use a different color for this. Let's use green. So what is x final if this is x initial? If I set x initial to be equal to 0, then x final is just going to be the total of delta x1, 2, and 3, basically. I'll say x initial equals 0, and x final will be delta x1 plus delta x2 plus delta x3. That's what they're asking for in part C. And then part D, how long does it take to come to rest? Part D is, it's just asking for T3. What is T3? I think I've messed this diagram up. If it weren't for the colors, it would be unreadable. I mean, even with the colors, it might not be all that readable. So what is T3? Okay, those are our 4 questions. And the twist actually occurs in the first one. The twist actually occurs in our first question. Oh, did I wrote that question mark on the page underneath. Okay, that can be quickly fixed. Yeah, there. Is that a better looking question mark? Probably not, but at least it's all contained within the same page now. Okay, let's see what we can do. So, we know delta x1 plus delta x2 is 17,500. We know the sled starts from rest. We don't know what delta x1 is, or delta x2 for that matter. Okay, let's see what we can write down before we decide on a solution path. So I know the times are related, and I know the displacements are related, so actually not too different from how I approached the previous problem. If there's a relationship between the displacements and a relationship between the times, then if I rewrite one of them in terms of the other, that's going to be two equations and two unknowns that I can solve. So let's see what we can do there. If I start with delta x1 plus delta x2 equals 17,500, delta x1 plus delta x2 equals 17,500, then I can go delta x1 is equal to v0 times t1 plus 1/2 the acceleration times t squared, or t1 squared rather, plus delta x2. Delta x2 is going to be v1 times t2 plus 1/2 a2 times t2 squared, and that's going to equal 17,500. Well, v0 times t1, that's 0 because it started from rest. The acceleration for phase 2 is 0, so that part is gone. So now I have v1, which we don't know yet, but they called it v, so we will rewrite it as just v. t2 we don't know yet. t1 we don't know yet. Looks like we're going to need another equation because we have three unknowns here. So I'm going to write 1/2 times a1. a1 is 40, so 1/2 times 40, that's 20. t1 squared plus v times t2 equals 17,500. I could just rewrite the t2 as 90 minus t1, but that wouldn't be enough unless I can do something with the v. So for the v, what can I do? If I were to use the first equation of kinematics, I would get v1 equals v0 plus acceleration 1 time 1. v1, again, we're just calling v because that's what the problem wants us to call it. And then v0 is 0, so that's gone. And then 40 times t1. Okay, there we go. So v equals 40 t1. We can plug that in here. And let's see what that does for us. Let me flip the lights on. So if I plug that in here, what do I get? Uh, 20 t1 squared plus 40 t1 goes in for v, and then times t2. 40 t1 times t2. And that all equals 17,500. Okay, now I've reduced it to just two unknowns in this equation, and I've got the same two unknowns in this equation over here, so I can put those together. I'm going to go ahead and solve for t2. t2 is equal to 90 minus t1, and then plug that in for t2 over here, so 20 t1 squared plus 40 t1 times t2 is 90 minus t1 equals 17,500. Okay, distribute the 40 t1 and I get 20 t1 squared plus 40 times 90 is 3,600 t1, and then minus t1 times positive 40 t1, that's minus 40 t1 squared. Okay, 20 t1 squared minus 40 t1 squared would be negative 20 t1 squared. And I want to actually add that over to the right-hand side so that it comes out positive, because I would rather have my squared terms be positives. So actually, I'm going to move everything from the left over to the right. So I'm going to have 0 on the left-hand side equals negative 20 t1 squared when moved to the right-hand side becomes positive 20 t1 squared, and then minus 3,600 t1, and then that was already positive 17,500. So now, I mean, they're still whole numbers, so there might be hope that you can just factor. If you divide everything by 20, what does that give us? That's going to give us, it's probably not going to help. I don't remember it helping, but we'll see. We get t1 squared minus, let's see, 3,600 divided by 20. So divided by 2 and divided by 10. Divided by 2 gives us 18, and dividing by 10 removes one of the zeros, so we still have the other one. And then 17,500 divided by 20. Remove a 0 and divide by 2. 1750, 875 if I'm not mistaken. Let me double check that one with my calculator. 17,500 divided by 20. 875. All right, I've still got it. Doesn't hurt to try and challenge yourself and see how far you can get without your calculator before you grab it. That actually helps you get better at detecting errors, because when you can at least estimate what your numbers should be coming out to, then when your calculator gives you the wrong answer because you pushed one too many buttons, you can probably catch it more easily that way. So yeah, mental math is not overrated. Anyway, factors of 875 that add up to negative 180. Good luck with that. Yeah, let's use quadratic formula for this. I guess my throat didn't like the mention of the quadratic formula. Let me take a sip of water. Okay. So, negative b, that's negative 180, plus or minus the square root of b squared minus 4ac, 4 times 1 times 875, all over 2a, all over 2 times 1. Okay, let's see what we get. So t1 equals negative 180 is positive 180. I'm going to start with plus square root 180 squared, and then minus 4 times 1 times 875, all over 2 times 1. In the plus case, I get 175, and in the minus case, I get 5. So I get 175 or 5. Oh, well, this is different. Every other time we had to solve for time using the quadratic formula, we had one positive answer and one negative answer, and we could just throw out the negative and that would be the end of it, because negative time doesn't really make sense for most of the problems we encounter. So if these are both positive results, does that mean we can't eliminate either of them? Well, not quite. If you say that, then you're forgetting something. T1 and T2 need to add up to 90 seconds. If T1 is 175 seconds, then that's implying that T1 is greater than the sum of both of these times, and that would require T2 to be negative, and that doesn't make sense. So we can eliminate the 175. It is not a valid result, despite being a positive for once. So T1 is equal to 5 seconds, which tells us then that T2 must be equal to 85 seconds for their total to be 90. And there's part A. Part B, solving for V. V is equal to 40 times T1, so 40 times 5, V is equal to 40 times 5 would be 200 feet per second. You might be in the habit of writing that as meters per second, so that's the one thing to watch out for with this problem. It uses different units. Be careful about that. Okay, part C. What is the final position if the sled is to slow down at 20 feet per second squared until it comes to a stop? What is the final position? Well, we know what the final velocity needs to be. It needs to be 0. And we know what the velocity is at the end of phase 2. It's a constant velocity for all of phase 2. It's what we just calculated. It's 200. So if it's at 200 feet per second this whole time, then it starts at 200 feet per second for phase 3 and loses 20 every second, so that should take 10 seconds. That's just the quick math, but of course we can also just use our traditional approach with our equations. V, I guess this would be over here, this would be V2, the way we name our velocities, and this would be V3 equals 0. V2 is just equal to V1 is equal to V. So V3 is equal to V2 plus acceleration of phase 3 times time of phase 3. Oh, actually, this is not the right equation to use. I'm solving part D. Okay, I mean, we can solve part D first. That's not a problem. Okay, so 0 equals 200 would be V2, plus acceleration, so plus negative 20 times T3. Add 20 T3 to both sides, divide both sides by 20. T3 is equal to 10 seconds. Okay, so we solved part D a little earlier than intended, no problem. We could then plug this into the second equation to solve for part C. Or we can act as if we did not just calculate the time and use the third equation instead. So what color have I not used in a while? I guess this purple color. So we can do V3 squared equals v2 squared plus 2 times acceleration 3 times delta x3. And that gives me 0 squared equals 200 squared plus 2 times negative 20 times delta x3. I'm not going to square the 200, actually. I'm not going to square it. However, I am going to subtract. Actually, no, I'm not going to subtract it. I'm going to add 40 delta x3 to the left-hand side. So 40 delta x3 equals 200 times 200. And if I divide one of those 200s by 40, then delta x3 equals, dividing by 40, that would be 5 times 200 equals 1,000 feet. And we already know that the first two parts of the trip totaled 17,500 feet. So add 1,000 feet to that, and x final would have to be 18,500 feet. I guess I skipped the step of writing x final equals delta x1 plus delta x2 plus delta x3. But you know, I would hope that you guys remember to write that on your exam papers, even though I tend to skip some of that stuff. All right, that takes care of the rocket-powered sled, and I think it is time to wrap up with the final question I have planned for today. It's not too complicated of a question, but it does nicely transition us to our upcoming topic. And then for homework, I guess I'm just going to have you guys read the material, watch the videos, all that stuff. Oh, come to think of it, I don't think I set up the scene for that in OBS. I'll have to work on that once we get to it. Anyway, next problem, our final problem for today, says, a stuntman sitting on a tree limb wishes to drop vertically onto a horse galloping under the tree. The constant speed of the horse is 10 meters per second, and the man is initially 3 meters above the level of the saddle. Part A, what must be the horizontal distance between the saddle and the limb when the man makes his move? And part B, how long is he in the air? I think we actually need to solve that first. I think we need to solve how long he's in the air first in order to be able to do part A. I think I warned about this before, but just in case I haven't, yes, you will sometimes be asked physics questions, whether it's in your textbook or on an exam, where you will be asked to solve things not necessarily in the order that they need to be solved in. Sometimes the thing that they ask for last is something you need to calculate earlier in the problem in order to solve some of the earlier things they ask for. Anyway, rambling aside, let's go ahead and draw this situation. So we have a horse. Let's see how well I can draw this horse. It's been a while. It's looking like a dinosaur so far. I mean, do I need to draw it perfectly? No, I could just as easily have drawn some oddly shaped block and called it a horse. Okay, and then that is not what even is that? That's not a horse. But we'll pretend it is. We'll pretend that thing is a horse and it is galloping at some sort of velocity. And there's a guy waiting in a tree, sitting atop a tree limb like so. And then I won't draw the rest of the tree, but let's draw the guy. So let's draw him in red. And the guy is sitting right here, stick figure. Guy is sitting here, and he's getting ready to drop onto the horse. And he needs to time his drop so that he actually lands on the horse saddle, and so that he can achieve a perfect landing. So he is 3 meters above the level of the saddle, so I guess I didn't draw a saddle here, but I don't even know how I could, with this level of drawing skill, I don't know, just pretend that's a saddle. And he's got 3 meters on that. He's sitting 3 meters above the level of the saddle. And the horse is moving at a constant speed of 10 meters per second. So V horse equals 10 meters per second, and acceleration of the horse, I guess that H kind of looks like an N, let's make it longer. Acceleration of the horse is 0. Horse is moving at a constant speed of 10 meters per second and in a constant direction, so constant velocity. What must be the horizontal distance between the saddle and the limb when the man makes his move? So that's their first question. What is this? What is this delta x? Once this guy sees the horse pass this mark, how far away is this mark from the tree in order to nail the perfect landing? And then part B, how much time is he in the air? We actually do need to calculate that first, because whatever this delta x is, that's how far the horse has to travel. And how far does the horse have to travel? Well, that would be delta x of the horse is equal to v of the horse times t plus 1/2 the acceleration of the horse times t squared. Well, the acceleration is 0, so delta x is just going to be v horse, which is 10 times t. Now, this t is not only the amount of time that it takes the horse to travel from here to here, but it also has to be exactly the amount of time with which this man drops. So this man has to time his drop exactly at this moment, so that, you press start on your stopwatch, the man begins dropping and the horse begins from here. Maybe the horse was moving before that point, but you start your stopwatch when the horse is at the right point and when the stuntman begins his drop. So they're under a shared stopwatch here. They would have the same time. So T horse equals T man equals just T. And I start the timer when this guy begins his drop. So, yeah, we actually do need to calculate what this t is, or else we can't go any further. That's the only way for us to get our delta x. Okay, so then let's go back to the man and figure out how much time it takes him to drop 3 meters. Well, he starts with no vertical velocity. He's just sitting until it's time for him to drop. So his initial vertical velocity is 0. V man initial is just 0. And we know his delta y has to be -3, right? He has to drop 3 meters. And we know his acceleration is just due to gravity, so acceleration of the man is -9.8 meters per second squared. That is enough information for us to calculate the time. It's also enough information for us to calculate his final velocity, but we don't need that. So to get the time, usually we would avoid using the second equation because it leads to a quadratic, but as you might remember from the other problem we did today, if your starting velocity is 0, we don't have to worry about that. Let me switch colors here. Let's do green. And let's do delta y man equals v man initial times t plus 1/2 the acceleration of the man times t squared. -3 equals, well, that's just going to be 0. And then 1/2 of -9.8 is -4.9. And then t squared. So cancel those negatives. 3 over 4.9 equals t squared. And if I take the square root of that, what do I get? 3 over 4.9 is about 0.612244. And if I take the square root of that number before I even round it, I get 0.78246. I'm just going to round that to 0.782. So I'm getting t equals 0.782 seconds. Okay. And then delta x, if I plug that in, 10 times 0.782 tells me delta x would have to be 7.82, and I guess that would have to be in meters, since the horse was moving in meters per second. And there we go. So on a test, what you would do is you would do this calculation. You would submit your answer as 7.82 meters for part B, or for part A rather. And then when you get to part B, you say t equals 0.782 seconds as shown in the calculations when solving part A, or something to that effect. And you would get full credit for that. So yeah, don't be too surprised. Don't assume just because they ask you something later in the problem that you have to wait until later to solve for it. Chances are, well, I don't want to say chances are, it's not always guaranteed, but sometimes there are some cases where you need to calculate those things ahead of when they are asked of you. So don't assume that you don't have to calculate them at all just because they don't get asked about until later in the problem. That's, I guess, one of the big takeaways from this. But the other takeaway is this actually helps us transition rather smoothly to the topic of projectile motion. Here we looked at two separate objects. I guess in physics we're always going to refer to them as objects, whether they're living things or not. But we looked at two separate objects, one moving in the horizontal dimension and one moving in the vertical dimension. In the upcoming chapter, we're going to do something similar to this, where we basically do the same thing. We track vertical motion and horizontal motion separately, but we do it all for a single object. So that is what's coming up next time. So let me go ahead and see what I would recommend you do in preparation for our upcoming chapter. Let me open this up and see. Okay, I did have it preset, so not too bad. Okay, let me put that up on the screen. Okay, so next time, projectile motion. We already talked about vectors. We talked about vector addition and vector decomposition and how to work with them. That's coming back. So if you feel like you're rusty on that because it's been too long since we did vectors, go back to Unit 0 and rewatch the stuff I did on that, or practice the practice material that's available for that topic, because we're going back to that. Pythagorean theorem, sines and cosines, this is going to be the rest of AP Physics, basically. You're going to be doing this in pretty much every single chapter, except, I guess, for Physics 1, you will not be doing this for the fluid chapters, for the fluids chapter. Actually, there might be a little bit of that. There might be a little bit of it, so I don't want to speak too soon. I still have to figure out how I plan to cover the fluids chapter, so we'll see. But just go ahead and preview. I would say look at this projectile overview. Go ahead and read the chapter sections in the book. So our book, remember, is this. It's linked right here in the top of the course plan. But yeah, go ahead and open that. Go to your two-dimensional kinematics. That's just another way to say projectile motion. And read sections 3.1 and what was it? And 3.4. Those would be the sections to read if you want to get an introduction. Watch the videos. I think this one is from Flipping Physics. And actually the second one also might be from Flipping Physics. And worked examples. And what I don't have here that I should list, I will put it in the description. I have a little PhET simulation project thing for you guys to look at. Actually, give me a minute. Let me switch screens and see if I can find it real quick. I should still have it somewhere over here. Where is it? Yeah, I'm gonna have to add it over to the course plan. Yeah, I'll put it there, but for now I'm just going to, let's see. How do I get, yeah, copy the link. It's an unlisted video of mine. So let me transition to it. Yeah, this would be the video. I guess you guys can't see the address bar over there. Let me just, yeah, if you want to manually copy that down, I'll try and be quick about just linking to it in the course plan, but there's the link to it if you're in a hurry and you want to see it right away. But I will definitely put it under the videos and resources. This is kind of like a self-guided project where I want you to experiment with the projectile motion simulation from PhET, P-H-E-T, PhET simulations. And it also has the link to the simulation. Do I link it? Yeah, it's linked in the description too. So yeah, those would be like your big homework assignments. With this project, you also want to dedicate some time to just understanding conceptually how air resistance changes things. But yeah, the more of this that you can get done before next time, the smoother things will go, the more easily you'll be able to digest information. I mean, I'm still going to go over everything anyway, but I feel like hearing it the second or the third time makes it more effective. So definitely pre-read, pre-watch to the best of your ability. If you can't get all of it done by next week, do as much as you can. And I think that is it. Do I have any other announcements? So hopefully next time will be just our normal Sunday schedule. Hopefully I don't have to postpone, what do I want to call this, an episode of Al's Physics 1 and Physics C lecture series. And yeah, I'm not gonna have the time to do my traditional office hours after this, so we'll just skip that and wait until next Sunday. For those who were waiting for that, sorry to disappoint, but the unexpected happened yesterday and I just couldn't find the time to squeeze that in for today. So yeah, that'll be the end for today. Take care, study hard, do your homework, and I will see you next week.